Everyone. So let's pick up where we left it with this theorem about interlacing, which is due to hammers. So let's quickly recall the notion of a quotient matrix for in that case. So I will tell you about hammers interlacing. So as before, we have a graph with vertex set V and edge set E, and we have a partition of the vertex set into M subsets, non-empty subsets. So assume that this is a partition of V. So like I said before, this partition doesn't have to be equitable. To this partition, we associate a quotient matrix. The quotient matrix B, let's say Bij of this partition is an M by M matrix, is defined as follows. The entry Bij equals the number of edges between Vi and Vj divided by the cardinality of Vi for any I and j between 1 and m. So this is the average number of neighbors that the vertices in Vi have, that the neighbors live in Vj. Okay? So the theorem that we want to prove states the following. One, the eigenvalues of this quotient matrix B interlace the eigenvalues of A okay, and two, if the interlacing is tight, this is what we defined this morning, then the partition pi is equitable. Okay. All right. So we want we had. I'm not going to write it again. The Courant-Hilbert theorem that we saw earlier this morning. We saw an application of Cauchy interlacing, and we'll see how Courant-Hilbert theorem will also be used here. So let me show you how that works. So as before, we will use this. The matrix, the characteristic matrix of a partition, where the columns are all the characteristic vectors of V1, V2, Vn. Okay, so denote by P the n by m characteristic of the partition pi. So maybe let me do it here, like to help us understand. I'll illustrate how this works by a small example. Okay, so let's say my graph gamma let's say is this graph just k4 minus an edge, something like this, and I have 1, 2, 3, 4. Okay, and let's say my partition V1 is 1, 2, and my partition V2 is 3, 4. Just happens to be equal, but in general they don't have to have equal size. Okay. I'm not going to write the adjacency matrix of A. We'll talk about how you can get its eigenvalues in a little bit, but let's see B. What will be, so B will be indexed by V1, V2, V1, V2. And now again, in the diagonal entry here, 1, 1, is going to be the average degree inside there, and it just happened, it's 1, okay? In the entry 1, 2, like I said, V1 is the one on the top, V2 is the one on the bottom. In the entry 1, 2, again, the easiest way may be just to count the edges and divide. So you see there are 3 edges and you divide by 2, so you get 3 over 2. Okay? And something similar will happen here. If you look from here, if you look up, you will see 3 edges and 2 vertices. So here it just happens to be symmetric, but it doesn't have to be. So you get 1. Okay? So that's 1. Let me give you one more example. So this is, let's say, B1 with this partition. Let me give you an example just so that I convince you that it doesn't have to be symmetric. Let's take the same graph. But now this is my, let me call it W1, and this is my W2. So just the 1 vertex here and 3 vertices here. So this one, I will call it B2. Inside here I have 0. Going this way, I see 2. Backwards, what's the entry? You have 2 edges, but you have 3 vertices here, so the average will be 2/3. And inside here, you see 2. Okay? So that's another quotient matrix for a different partition. Okay? Okay. Okay, so this n by m is something tall like this, as we talked before, and each part corresponds to V1, Vm. They're the characteristic vectors of V1, V2, Vm. Okay? So as we talked before, the columns of this matrix P are orthogonal. Okay. Here, for example, the matrix P here, you're going to have 4 vertices and 1, 2, 3, 4, and this is V1, this is V2. So you have 1 and 2, so it's 1, 1, 0, 0, and then you have 0, 0, 1, 1. Here, the matrix here, let's say P2, you will have W1, W2, the same labeling 1, 2, 3, 4, you have 1, 0, 0, 0, 0, 1, 1. Okay, that's all. Okay, now, if you remember, in the proof of Courant-Hilbert theorem, there was this matrix S. So we're going to need to cook up a matrix S. Now, the matrix S, what property did it have? Columns were orthonormal. Here, the columns are orthogonal. So we're going to make something, we're going to normalize this. I mean, there's not much normalization we have to do because already the distinct columns are perpendicular to each other. So we just have to normalize each of the columns so that they they have length 1. So let me see how we do that. Okay, so first let's write this. We have that P transpose P. We've seen this, we've done this calculation a few times, is going to be the diagonal with the cardinality of V1, cardinality of Vm, the diagonal matrix where you have the cardinalities on the diagonal because the columns are orthogonal. And this will equal some matrix D square, where D is the diagonal matrix where you have the square roots of the cardinalities. Square root of cardinality of V1, square root of cardinality of Vm. Okay, now this one, because the parts are non-empty, this will be invertible. You know this. And what we'll do is we normalize now the P and we say define R to be P times D inverse. So D inverse is going to be, instead of square root, you have 1 over square root. So just try to figure out your matrix multiplication in your heads. But essentially this this R, what it does, it normalizes each column. It's each column of P is normalized. And then what do we want to show about this R? So then R transpose R equals identity of M. So what number are we?
20.
Okay, well, we were 21, now we're 22. So exercise 22. So do this calculation. D minus 1, P transpose P, diagonal, they kill each other. Okay? Okay? All right. So now we got our matrix R. We have our matrix A. So we can just say by Courant-Hilbert theorem, the eigenvalues of R transpose AR interlace the eigenvalues of A. Now this R transpose AR, we don't know what it is. I mean, you can calculate it, but I don't know if it will be B. Let's keep the B somewhere. So let me write here B. Okay, so the goal now is to somehow relate the matrix here with the matrix here. Okay, so this is, this falls into your lap because you have a partition. Okay, I have this big tool, big hammer, which is Courant-Hilbert theorem. Okay, I already have my adjacency matrix A. I have the partition. The partition gives me this matrix whose columns are orthogonal. But for Courant-Hilbert, I need a matrix whose columns are orthonormal. So you just do that. Okay, you apply it, and you get R transpose AR interlace A. But now R transpose AR, it's a little bit, can try to figure out what it is, and you have to figure out what it is with respect to B. So the thing that we haven't done is to figure out what B is. So you remember we did some calculation, I think yesterday, we calculated something like P transpose AP for this characteristic matrix when we're doing like equitable stuff. So if you do that calculation, you will get a matrix is going to be M by M, where you're going to keep count the number of edges between the parts. But now my matrix B has the number of edges between the parts, but it's normalized by this. Okay? So what happens is that the matrix B will be something like P transpose P inverse. P transpose P will be this diagonal of the cardinalities of the set V. And when I do inverse, I just introduce this thing. So the matrix B will be P transpose P inverse times P transpose AP. Something like this. Okay, so this is the key. So on one hand, you have Courant-Hilbert theorem, R transpose AR with A, and now somehow what I want to get to, I want to relate B to this R transpose AR. And in order to relate B to this R transpose AR, first I need to get my hands on B. which is this, and then you can write it as if you want, D minus 2 P transpose AP. Because D, you see, P transpose P is D squared, you take the inverse is D to the minus 2. I know, it's a lot. So, okay. So now let's rewrite R transpose AR a little bit. So R is PD minus 1. So you'll have PD minus 1 transpose A R, which is PD minus 1. Okay. On this side, you're going to leave it like this because it kind of looks like AP. You have AP here, so you leave it like that. Now, here it's a transpose. You take the transpose. Now, you're lucky here because D minus 1 is a diagonal matrix, so it's going to stay the same. So it's D minus 1, P transpose A, P, D minus 1. So it's not quite B, but it's almost. It's just like, what can I do? Maybe what can I do to B to make it into this? You see, they both have this part here, but it's just this D minus 1, like this R transpose AR has them on this side, the other one has it, you know, something like that. So let's do D times B times D inverse. So then we get D, we have the formula there, D minus 1 P transpose AP times D. No, this one is D, okay, I haven't, let me see, so I don't need to, yeah, D minus 2, I'm sorry, yeah, thank you. D minus 2 P, P, and I have a D minus 1 on this side. Yes, D minus 1 is D minus 1 P transpose AP, D minus 1, which is exactly this one. So dVd minus 1 will equal R transpose AR. So what can you say about, so B and this matrix are similar, so therefore B and R transpose AR are similar. So if they're similar, they have the same eigenvalues, and if the eigenvalues of this interlace the eigenvalues of A, the eigenvalues of B will interlace the eigenvalues of A, because they're the same as that one. Okay. The second part, so this is the proof. So there are two main ingredients. One, you have to know this big canon, big hammer, the Courant-Hilbert theorem. So you have A, you want to find some smaller matrix that interlaces its eigenvalues. So you need to multiply, find some kind of orthonormal matrix, okay? From the partition matrix, you get an orthogonal matrix pretty much for free by these characteristic vectors. And you just normalize that matrix and kind of, you know, it works. So that's the idea. Okay. I will not give you the proof of the other part because we have some things to go through, but let me give you a quick application of this theorem. Okay. But I will use the second part about interlacing is tight and all that. I will use it when I have the equality case of this theorem. So let me give you this theorem. This is called Hoffman's ratio bound, Hoffman bound, ratio bound. There is like a whole book written about applying this bound to various graphs. You can find more. There's an article by Wilhelm Hemmers I think you should be able to find it online, about the history of this bound, the history about the Hoffman ratio bound. And this is a recent paper, Hoffman's ratio bound. Because throughout the years, this bound was been attributed to other people and so on, and you know, William Hammers, he writes down all his recollections about it, so you'll get math with a little bit of history. So it's an interesting thing. Okay, so what is this bound? This is a bound for the independence number of a graph again. So let gamma be a k-regular graph with n vertices and eigenvalues. So these are the eigenvalues of the adjacency matrix. K is the largest one, greater or equal to lambda n. So lambda n is the smallest. Okay. Then the independence number of the graph, so this maximum number of vertices such that no two are adjacent, is bounded from above. So here again I'll take k to be, this k is going to be greater or equal to 1, so that we avoid trivialities. So this will be less than or equal than n times minus lambda n divided by k minus lambda n. So you can kind of see why it's called a ratio bound, because you have a ratio here. Now, something that may trip you up a little bit is that you're seeing negatives things. So this independence number of the graph will be a positive number. It's the maximum number of vertices in an independent set. Now here, this graph, because k is greater or equal to 1, the graph has edges. And when you have edges, lambda 1 is positive, and therefore lambda n is negative. So minus n is actually positive. So if I want it to be less scary, I can do it like this. I can put absolute value of lambda n. So sometimes you will see like this. And again, at the bottom also, I can make it less scary. I can do plus this. And you can, if you do it like in this way, you can see that this number, this ratio, lambda, absolute value of lambda n divided by k plus absolute value of lambda n is strictly less than 1. So this gives you some upper bound less than the trivial bound of n. You know, you have it. Just okay. Okay. So let me show you how to prove this. And so this is the first part. There is a second part about equality, but I will do it after I give you the proof. Okay? So as before, let's take let S be an independent set of size alpha of gamma. So you take an independent set. We did it before. We took S and largest independent set, one of them. When we applied Cauchy interlacing, we looked straight into the adjacency matrix and we saw this big block of 0, and we used Cauchy interlacing to say something about this parameter being bounded by number of non-negative, non-positive, or all that stuff. Okay? Now here we'll do something different. So let me show you the picture, what we'll do here. So what you have here, you have this set S where there are no edges, and you'll have the rest of the world V minus. So these are the antisocial, okay, vertices. Nothing happens in between. And then this is the real world, okay? So now this suggests a kind of a partition into S and V minus S, okay? So that's what we're gonna do. We're gonna take this partition into two sets, S and V minus S. We'll calculate this quotient matrix. We'll calculate these eigenvalues. We're gonna say, okay, Hamer's interlacing tells us that we have some kind of interlacing, and we'll try to see what happens. What does it mean, okay? So that's what I will say. Consider the partition V equals S, V minus S, the quotient, so this is what we'll figure out first. The quotient matrix of this partition is the following. So I'll call it B, and before I'm trying to do any interlacing, obviously before I want to use any eigenvalues, I need to have a matrix. I need this matrix, this quotient matrix. So let's figure out what this is. First of all, how big is this matrix? 2 by 2. Okay, how hard can it be? So this is S, this is V minus S. So usually when I did it in the examples, I always started from here and so on, but I won't start from here. I'll start slightly off, because here's the thing. If I have a vertex here, my graph is K regular. This vertex doesn't want to talk with any of these vertices here. So where are all these vertices friends? They're going to be here. So which entry in this matrix is going to be K? 1, 2. And actually, I should have started here, because here I know what it is. What should be? 0. Very good. First row. Now, what comes after first row? Second row. Very good. Yeah. So we have to do. We have to go look what happens this way. But now here, this way, in the entry 2, 1, think about it in that form. Entry 2, 1 is the number of edges between the parts divided by the cardinality on this size. Can you tell me how many edges do you have between the parts? K times cardinality of S. So I will just shorten this thing to alpha. So I will have K alpha, because here I have alpha vertices, so cardinality of S is alpha. Everyone has K neighbors this way, so between here I have K alpha edges. And now I have to divide by this size. How much is this size? N minus alpha. I'm almost done. What about the entry 2, 2? Here. Yeah, something like this. So you can, because you know that you're losing K alpha, you're losing this out, and the graph is K regular, the thing here will be actually K minus this value, minus K alpha divided by N minus alpha. Okay, let me do it separately, so that maybe. So let's do it separately, so that so this is S, this is V minus S. In between, I know I have K alpha, okay? What do I want to calculate? I want to calculate the average degree inside here. So if I have a vertex here, X, so the antisocial ones were here, this vertex X will have some neighbors inside here. Let me call it T of X. And we will have some neighbors outside, okay? Which is obviously the remaining, which is obviously K minus T of X, okay? So the entry in the position 2, 2, what is it in terms of this T of X? Yes, it's gonna be the average here, so it will be the sum over all X in V minus S of T of X, divided by how many of them are there? N minus alpha, because we know how much. Now, when you sum this number, maybe I should have done it let me call this actually S of X, just for, you know what it is, but I'll just call it S of X, okay? Each of these T of X plus S of X equals K. So I can write this as summation over all X in V minus S, K minus S of X. And now, this will be split into 2, it will be summation k for all v minus s. That will be k times n minus alpha divided by n minus alpha. And then all these minus will be minus summation over all x in v minus s of x divided by n minus alpha. So here, this is k minus, here this is n minus alpha. But now, when you sum over all these vertices here, when you sum all their neighbors that live in here, what do you get? You just get the number of edges in between, which you know what it is. It's k alpha. Okay? So this is something standard whenever whenever you sum up the degrees in some induced subgraph, you have to take care of what happens the leftover. Like there's something that there will be some edges going out and so on that you have to be careful. Okay, so that takes care of the matrix. Yes.
For the matrix B, the row sum should
very good. So this will always happen. So if you have a k regular graph, and you take any quotient matrix that you want, and you define the entries of the quotient matrix the way we did, the row sums will always be k. The row sums will always be k. Okay. So now. Okay, your colleague is helping us here. Row sums are k, so therefore lambda 1 of b is k. So we won't get much information out of that. But what is lambda 2 of b? Which is the same thing. In this case, you see, in this case, the m that we use in our proof of interlacing is 2. So this is the same thing as lambda m of b, and this will be how much?
K alpha.
Minus. It's minus k alpha n minus alpha. So it's a negative. There's not much I can do with this. Lambda 1 is k. Well, you can apply everything you want. It's not going to help you anything. But the other thing helps me. Okay, the other value. So by Hammer's interlacing. And what you use Hammer's interlacing, you use the one on the end side of it. So you look at this lambda 2 as being the smallest eigenvalue of this small matrix. So what will happen is that this smallest eigenvalue of B is going to be greater or equal than lambda n of A, which I call lambda n. So it's the kind of the other type of inequality that's in the interlacing, okay? So the big matrix gets to lose this time to the small matrix, okay? So now let's write down what this means. Therefore, minus k alpha n minus alpha is greater or equal than lambda n. And now you just have to, what is our object of interest? Which number we want to go after? Alpha. So we have to do something here and just make sure you don't change sign, you make mistakes. So here, n minus alpha is positive, so I can move it there. So I will have minus k alpha greater or equal to n lambda n minus alpha lambda n. And you have to remember, so I just cross multiply. N minus alpha went here, n lambda n minus alpha lambda n. Now, I need alpha on one side, so I will move the k alpha here, I will move the n alpha here. So I will get minus n alpha, which is n times, minus n lambda n, which is n like this, greater or equal than k alpha minus alpha lambda n. And we're almost there. You write this as alpha times k minus lambda n. K minus lambda n is positive, so you divide by it, so you get n minus lambda n, k minus lambda n, greater or equal to. Okay. So it's the simplest partition that you can think into two parts, independent set. And you can do something more general. You can apply it not just to independent sets. You can this will give you information about the average degree inside a set of vertices, if you want, in terms of the number of vertices and the eigenvalues. Okay. All right. So let me give you some examples where you can apply this, because we've done like some small example of eigenvalues. That's what I'll use for this part. Let me see what I can erase. I'll erase here. So yesterday I showed you how with the Peterson graph you have here the eigenvalues are what? 3, 1, minus 2. 3 has multiplicity 1. 1 has multiplicity, well, I don't know. I haven't proved that, but I'll do that. Okay, so we just showed that the eigenvalues are 3, 1, and minus 2. Okay, so this is my k. This is my lambda 10, because n is 10 here, the smallest. So you just apply it here. So you say alpha of Peterson, let's call it that, is less than or equal than, you first rewrite this, n minus lambda n, k minus lambda n, and then you write it's 10 times, this will be 2, k is 3 minus minus 2. So you get 20 over 5 is 4. Okay? So it's at most 4. Yesterday I showed you an independent set of size 3, but you can see here that I can pick a different one here. I have 4 vertices. This is independent set, and this is maximum because I'm guaranteed that there's nothing bigger. I mean, for Peterson graph, you can try to do it by hand. You can do it, but I just wanted to show you this. Okay. Maybe I'll do it now since we're at the Peterson graph. Let's quickly do the other bound to see the Kvetovich bound, the one about inertia. Let's try to do that as well. But for that one, I need to know the multiplicities of these eigenvalues, because I need to know how many, you know, I have 3, 1, and minus 2, but I don't know how many 1s I have, and I don't know how many 2s. So let me call this multiplicity f, and this multiplicity g, and this one I know because the graph is connected, the multiplicity is 1. So if I want to find f and g, f plus g equals 9, because 1 plus f plus g should be 10, because that's, yeah. And where else do I find one more equation about f and g? We've done it before, we've looked at it. The trace. So you can look at the trace. So the trace of the adjacency matrix is 0, but it will be the sum of the eigenvalues. 3 comes with multiplicity 1, so 3 times 1, plus 1 times f, plus minus 2 times g. Okay, so I get that f minus 2g equals minus 3. And if you subtract from the first equation, you subtract the second equation, you get 3g equals 12. So this will be 4, and this will be 5. So g will be 4, f will be 5, and g will be 4. Okay? So now, if you apply the inertia bound, the one that we did this morning, at most, minimum. So first, let's figure out what the numbers are. N is 10. What's a n plus, and what is n minus? What's the number of positive eigenvalues? What's the number of negative? 6 and 10. 6 and 4, sorry, 6 and 4. And then this one is the maximum of the differences, so the minimum. So the minimum will be the minimum of 10 minus 6, 10 minus 4, which is 4. So in this case, it works both ways. Okay. Now, there are many graphs on which you know, these bounds get equality, but obviously they're not. There are also many graphs on which they don't give you what you want. One thing I will tell you here is what happens if you have equality, because that's important. So equality happens here if and only if this partition that you have here is equitable. This partition S V minus S is equitable. And there is another characterization of equality which I won't give you here, in which it tells you that equality happens if and only if a vector which is related to the characteristic vector of S belongs to the eigenspace of lambda n. And that's what is used also in characterizing equality for this inequality in many situations. Okay? So in general, applying this bound, it will be like kind of somewhat the easier part. The harder part will be in the equality case when you want to analyze what happens if you have equality. Okay? So you can play with this if you have graphs, regular graphs, but the other thing is this is for regular graphs, and you know, you can try to play with for some graphs. Whenever you're looking for independence number, you can get something like this. Okay. Let me tell you one more thing about this, and then I'll give you a proof of. Yes, question.
Which partition?
The partition. So the partition into any independent set of maximum size, and the rest will always be equitable. Okay. Yeah. Okay. What was I saying? What do I need to give? I wanted to do something before.
That is what he said.
Eh?
That is what he said. You are going to do something.
Yes, but I forgot what I said. Oh, yes. So let me tell you one more thing about this. So also a consequence of this theorem, so corollary, if gamma is k regular, then I haven't defined this, but I'll define chi of gamma, which is a chromatic number of gamma, is going to be greater or equal than 1 plus k divided by absolute value of lambda n, where chi of gamma is the chromatic number. So chi of gamma, so it's the, okay, in case not everybody knows, so chi of gamma is the minimum, I don't know, let's call it t, such that we can partition, there is a partition of v into t parts, v1 blah blah vt, vt, such that all these parts are antisocial. So all these parts are independent sets, such that v1, vt are independent sets. So you can have edges between the parts, but you cannot have any edges inside. It's equivalently, it's the minimum number of colors that you can color the vertices of the graph, such that any two adjacent vertices get different colors. So here, the vertices here in V1 will get the same color, and there's no problem. So color classes are usually independent sets, are always independent sets. So, yeah. And so, when you have this, let's say t, if t is the chromatic number of gamma, the number of vertices in gamma n is cardinality of v. It's the sum of all I1 to t of cardinality of vi. Each of vi is independent set, so its cardinality is going to be less than this alpha of gamma. So what you get here is T times alpha of gamma, which is the chromatic number of gamma times alpha of gamma. So if you write it in terms of chi of gamma, you get that chi of gamma is greater or equal than n divided by alpha of gamma. So if you use, this is a combinatorial inequality, if you use this inequality with this inequality, it gives you this bound. That's all. So, okay. There's something more general here for this problem, for graphs that are not necessarily regular, but I'm not going to do that right now. Okay. Okay? Okay. So I plan to do something else for the remaining part of the, so how much time do I have? 20 minutes? 10 minutes? 15 minutes. So I will, I will be nice and not ask you to erase the board for a change. So yeah, you're welcome. And then, so take this time to catch your breath, get some water, and then I'll tell you something else about matrix 3 theorem, which is about Laplacian matrix that Professor Kanan talked about. So. Okay, so I'll change gear and I'll talk about something else. As before, we have gamma dE. So let me give you some quick definitions. What is a spanning subgraph of gamma? A spanning subgraph of gamma is obviously a subgraph of gamma, but it is the one in which you keep all the vertices. So you just delete some edges. So it's a subgraph of gamma whose vertex set is V. And then second, what is a spanning tree of gamma? Well, surprise, surprise, it's a spanning subgraph that is a tree. That's all it is. Okay, so we have this example that we carried with us, the bow tie, friendship graphs. I don't know if the labeling is the same. We have this, okay? So now what we're interested in this parameter tau of gamma, which is the number of spanning trees. Of gamma. So here my graph is labeled, so I'm looking to count all the labeled spanning trees. Some of them may be isomorphic, but as unlabeled things, but I don't care. So for something like this, I keep the vertices, and what do I need to do? I need to destroy the cycles, and so you can see this is a spanning tree, but there are more. Okay, there are more spanning trees and so on. How many do you have in total? I'll give you like 10 minutes. No, we don't have 10 minutes. So, okay. So this is the theorem in, so let me write down the Laplacian matrix here. The Laplacian matrix here, we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1 has degree 2. 2 has degree 2, 3 has degree 4, and then 2 and 2. And then 1 is adjacent to 2, so -1, -1, 0, 0. Oh, sorry. 1 is adjacent to 3. Thank you. Oh, thank you. Yes, you're right. Okay, here I have again this, and here I have -1, -1, -1, -1, -1. Okay, so what you do, you pick your favorite or your least favorite row, least favorite column. Okay, let's say they're the same. First and first, okay, because you want to destroy things early. Delete this, delete this. You get a 4 by 4 matrix here, which I call L11. Take the determinant, and that's your answer. Isn't that like magic? What kind of sorcery is this, you know? So this is what people call Kirchhoff matrix tree theorem. And there are many versions of it. The one that I will give you is just this, that tau of gamma is the determinant of L, and I'll just put here x, x. So by this, I mean is the matrix L without row x and column x. How can it be? Okay, so we'll do it in a few steps. So earlier, Professor Kanan introduced the incidence matrix. I forget it was Q transpose or Q transpose Q? Q transpose. Okay, now you need some properties about this matrix Q. So one property of the matrix Q is every square submatrix of Q has determinant 0, -1, or 1. Very convenient, okay? Let me do the matrix here. So the way I will I'll do the orientation, I'll orient from smallest number to bigger number. So I don't need to do the arrows, so I'll just do the edges. So I have here 1, 2, 3, 4, 5. And here I'll do the edges lexicographically, 1, 2, 1, 3, 2, 3, 3, 4, 3, 5. And the first one I get a plus, the second one I get a minus. So which one? 4, 5. Thank you, thank you, thank you. So 1, 2, 1, -1, 0, 0, 0. 1, 0, -1, 0, 0, 0, 0, 1, -1, 0, 0. You can do it in how many ways? How many incidence matrices you have once you fix the labeling here and the labeling here? You just have to pick an orientation on each edge. So it's 2 to the power of the number of edges. So, okay, so I'll just give you one here. Okay, so to prove that every square submatrix has determinant 0, 1, or -1, you use induction on the size of the matrix. If the submatrix is 1 by 1, I can prove it, because the matrix is 0, 1, -1, so that's clear, okay? Now, if we do the induction step, assume that we have some submatrix, and let's see what happens. So let's see we're lucky and we pick this submatrix. If we have like columns or a row of 0, if we have a column of 0, then we're happy because determinant is 0. What happens if we have something like here where every column has 2 non-zero entries? We're also happy or we're sad? We're happy because this is, you know, the rows are not are linearly dependent, so the determinant here is also 0. Because 1, -1, -1, 1, 1, -1, so that's it. So therefore, the only case that remains, if we have one row, let me see if I can find something like here. If we have one column in which we have exactly one non-zero entry, that non-zero entry, what has to be? 1 or -1. So if you expand according to that column, you're getting a 1 plus a smaller determinant, but your smaller determinant is 1, -1, 0, so you're done. Okay? So this is very useful. Now, here, this is for connected graphs. So remember that the rank of Q is n minus 1. Professor Kanan proved this. Now, the third thing is, I erase my, let me do it here. So this matrix is what I call a fat matrix, because you have more columns than you have, in general, than you have rows. So here you have n vertices. Here you're gonna, let me pick a set F, cardinality of F, n minus 1 of edges. I pick n minus 1 edges. So I get this weird matrix that is going to be tall, like n vertices, n rows, n minus 1 columns. I claim that if I delete any row, this matrix here is invertible. Okay, why is that? So let's say first I don't delete this row. Here I have, well, it's invertible. No. Invertible, no wonder that you look funny at me. If and only if the graph with V and F is a spanning tree. So that's how the spanning tree come into play. They start playing. So first, let's say we have all the vertices. Here, let's say we have F, all the edges, okay? If this is a spanning tree, then this is an incidence matrix for that spanning tree, because I have all the vertices and I just have the edges. But the spanning tree is connected, so what should be the rank of it? N minus 1. Now the rows of this matrix, they add up to 0 all the time. So any subset of n minus 1 rows will be a basis. So if you delete one row, the remaining ones are linearly independent, so you're done. Okay? So that's the argument here. And so invertible will also mean that the determinant of such matrix will be what? Plus or minus 1. Okay? So then what the third ingredient is some big hammer, which is sometimes called Binet-Cauchy, sometimes called Cauchy-Binet. It may be called something else. So if you take this determinant of Lxx, which is going to be the determinant of this Q matrix in which you do something with X and you do something with X, like you delete the row X from Q and the column X from Q transpose, and it's going to be a summation of some kind of determinants of such matrices from here square for all F in F of cardinality n minus 1. So what will you pick up in this sum? For every F that is a spanning tree, you will pick up a determinant that is minus 1 or 1, but somehow you're lucky that it's squared, so you pick up a 1 and you get your answer. So that's kind of the proof of Kirchhoff matrix T theorem in 15 minutes, 10 minutes or something like that. So this is the proof that is given in Biggs' book, Algebraic Graph Theory. And I'll send you, in a day or two, I will send you some write-up in which I'll give you the write-up of this, which you can read at length, not in like 10, 15 minutes like we're doing now. Okay, so I'll stop here now. Thank you.
You can say about the bijective proofs, the difficulty of counting the spanning trees.
I mean, you can do